Hi there, welcome to a bonus video to part 5 of our LOGIG series. In this video we're going to look at De Morgan's laws, which we saw back in part 3, but now we're going to look at them a bit closer and some of the things we have to consider when we are deriving them. De Morgan's laws show some basic logical equivalences that are fairly intuitive to understand in natural language. Both of these are biconditional relationships. The first law says that not P and Q implies not P or not Q, and vice versa. In other words, if the conjunction of the two is false, then one of those two must be false, and vice versa. The second law states that not P or Q implies not P and not Q, and vice versa. In other words, if the disjunction of the two is false, then neither one of them can be true, and vice versa. Let's look at the truth tables for these laws. Feel free to pause with each table and work through it for yourself if you like, but spoiler alert, De Morgan knew what he was doing, so I'll go through these pretty quickly. For the first law, we can fill in the P and not P columns as well as Q and not Q, and then work through the connectives in reverse order. First, we look at the conjunction in brackets on the left, and then we negate that, and finally deal with the disjunction on the other side. We now have the final outputs on the left and right hand side, and we can see that on no line does a true input lead to a false output. The corresponding conditional is a tautology. If we look at the reverse direction, we have the same result. Nowhere does a true input lead to a false output. This is because all lines on the table have the same value on both sides. That is, they either have true on both sides or they have false on both sides. If this were not the case, then this could not be a biconditional relationship, because false into true in one direction, which is fine, would be true into false on the other, which is not. Very quickly, we can see that the same is true for the second law, and in fact both tables are fairly similar, although not identical. In both cases though, the outputs of the left and right sides have the same truth value, and so De Morgan's laws are valid tautologies in both directions. That means there are valid derivations for them in both directions using our syntactic calculus. Feel free to pause again now and work through those derivations for yourself. This will be considerably harder than the truth tables we've just looked at. I will do the derivations in the following slides, and I'm pretty confident I've got them all correct, but any real logic tutors, please correct me in the comments if you see that I've screwed up. For this first proof, I will say there are quite a lot of negations, so go carefully and confirm your understanding step by step. We start with the left-hand side of our first law, not P and Q. We use brackets to avoid an ambiguity, and we'll assume the negation of our intended conclusion and try to work towards the negation introduction, or reductio ad absurdum. However, this does not give us a way to disprove our hypothesis immediately, so let's assume one of the disjuncts, not P, and from this we can introduce not P or not Q. Now we have both not P or not Q and not P or not Q. This is a contradiction, and so we can reject a premise. You might think that we want to reject our first hypothesis on line 2. Well, we could do that, but that would still leave us dependent on our second hypothesis, not P. We would therefore have proved the trivial not P and Q and not P, therefore not P or not Q. So, to continue towards our intended goal, we reject our second hypothesis, giving us not P and therefore P via the negation elimination rule. We now do the same thing again with Q. We assume not Q, introduce a disjunction, and then a contradictory conjunction. And now we reject our third hypothesis, line 8, giving us not Q, and therefore Q. We have now validly derived both P and Q, so we can introduce the conjunction of them, and this gives us another contradiction, P and Q, and not P and Q. Here, we're allowed to reject another premise, and now we reject the hypothesis on line 2, giving us not P or not Q. In other words, not P or not Q. Note, in some versions of this derivation, you will see them take a final step, which is to introduce the whole proof as a conditional, which now rests on no premises. I will not do this every time, but it does demonstrate that each of these 4 derivations stands on its own based on no further premises. A final point of interest, when we reach the contradiction on line 14, we could reject not P and Q, and therefore affirm P and Q. This would prove the sequent that not P or not Q entails P and Q, which is another fairly intuitive true idea. If it is not true that at least one of them is untrue, then both of them must be true. In this case, line 1 would actually now be a hypothesis and line 2 would actually be our premise, but that is not the derivation that we have done here. To go back the other way, we will start from the disjunction, and so we'll likely be using the disjunction elimination rule somewhere. First, however, we will assume P and Q, which is technically the negation of our intended conclusion, because it is logically equivalent to not P and Q. From this, we can now get P alone and Q alone in 2 separate conjunction eliminations. And now we move on to our disjunction elimination. First, we assume not P as a hypothesis, which gives us a contradiction and allows us to reject line 2 from one side. Then we do the same thing on the other side by assuming not Q, contradiction, rejection, and we've now rejected line 2 independently using each side of our original disjunction. This allows us to use disjunction elimination in our final step to validly get the negation not P and Q, based on the disjunction itself, line 1, and no longer from the individual disjuncts, lines 5 and 8. And this concludes our derivations of the first law in both directions. The next derivation is the most straightforward. We start with not P or Q as a premise and introduce P as our hypothesis. With P, we can introduce P or Q, and now we can claim P or Q and not P or Q, a contradiction. This lets us reject a premise and we reject our hypothesis P. We can now introduce not P. We do exactly the same thing by assuming Q and creating exactly the same contradiction, P or Q and not P or Q, and then we can get not Q. We can now introduce not P and not Q, and a derivation is complete in the first direction. However, if our last derivation was the easiest to explain, then deriving back again is the hardest, and I will say I am not completely confident in my explanation here. I also want to thank a couple of users on Math Stack Exchange for asking and answering the relevant question. We'll get back to that in a moment. We'll start with our premise not P and not Q, but since we wish to show that not P or Q is true, we'll also assume the negation of that, P or Q, and aim for negation introduction somewhere down the line. We'll also take not P out of the conjunction. We'll save not Q for later on. As we are trying to negate a disjunction here, we must show that both sides of the disjunction lead to a contradiction. So first we'll assume P, and now we have P and not P, a contradiction. So we could just negate line 4, but that is not what we're going to do. First we're going to assume not Q, and this is the step where it gets tricky. We could validly get not Q from line 1, but we're going to need it later, so we will assume it as a premise. I will come back to this, but let's finish the derivation first. We'll now introduce the contradiction P and not P, and use this to negate our assumption not Q. This gives us not Q, and therefore Q. On the other side of the disjunction, we assume Q, and so we have Q. We have now derived Q from both sides of the disjunction, P or Q, so we're allowed to introduce Q based on the disjunction itself. We now use conjunction elimination again to get not Q from line 1, and what do you know? We have another contradiction, Q and not Q. And it's this contradiction we use to negate line 2, not P or Q, and we've successfully arrived at our goal. This is the end of our derivation. So what's going on here, and how does it help us to assume not Q at line 5? I struggle with explaining this intuitively, but I'll do my best. The part of the derivation from line 2 to line 8 is called a disjunctive syllogism, which takes the form P or Q, not P, therefore Q. When we put it like this, it sounds completely obvious. If P or Q is true and not P is true, then Q must be true. In formal terms, if we have not P and P or Q, then we either have not P and P, or we have not P and Q. And the first of those is a contradiction. We are distributing not P and over the bracket, just like in other forms of arithmetic. Be careful though, not everything has this distributive property. But how do we derive it? It's all based on making the assumption of not Q at line 5 and then using that to get Q. But why are we allowed to do that? Here is a question by Crystal Gamer on Math Stack Exchange, and they're asking why this assumption is valid, and if it is, why can't we just assume Q right away? The short answer is we do at line 9, and this is the second part of our disjunction elimination. However, for the first part, we must still derive Q from P, and to do that we need not Q. We use this to make another contradiction to reach our final goal, and it's the goal here that is important. Here is the answer given by user 14972, and this is how they start their reply. The thing you're overlooking is that you have a goal you're trying to reach. We're allowed to close the subproof in any valid way that gets us closer to the goal that we have. Great. But why does it help us at all? Why does introducing and then immediately negating line 5 get us closer to the goal, and why is it valid for us to do this? The answer is that it's valid exactly because it is not invalid. User 14972 talks about explosion and the fact that you can derive literally anything validly from a contradiction. In the same way then, you can kind of derive anything into a contradiction, and I'm sure that real logicians will disagree with my phrasing there. But this is why we can negate not Q using P and not P, and we can say for sure in this that we will not be led from true premises to a false conclusion. But that's all we can say. We mentioned all the way back in part 2 that there is kind of a wrinkle around the validity of the conditional, and here it is again. We know for sure that we are not on the second line of the conditional, but we don't really know which of the other 3 lines we are on. And here I want to address the one thing that Crystal Gamer did not get answered. Does this have any implications in non-abstract cases? Well, Crystal Gamer, 5 years later, in my opinion, this has the unfortunate consequence that we've spoken about before. You can never use logic to correctly identify value judgments, and this seems to come out of this wrinkle in the conditional. Is this conclusion something that is true and well argued, false and badly argued? Is it true but badly argued, or is it false but the argument is missing a premise so that it appears to be a good argument? This is what happens when someone offers a bad argument in good faith. They think they're on line 1 of the conditional table, but they are really on line 2. Values are things that we take to be true as a matter of faith. We simply assume that if there are any premises to our belief, then they must all be true premises. Note, I have not necessarily claimed that value judgments themselves do not exist, only that we cannot use logic to identify them beyond doubt. Which kind of sucks, but there you are. Finally, here is an incorrect version of our final derivation, from not P and not Q to not P or Q. Where does this derivation fail? This table is mostly correct. Just one tiny change reveals the mistake, and it is in the final step. When we use the disjunction elimination, we genuinely do remove premises 5 and 8 from the validity, but we reintroduce line 4, which we're not supposed to do. We can recall that the disjunction elimination is badly named because the result does depend on the disjunction. It just eliminates the disjuncts individually. This is an easy mistake to make for that very reason, but there are many other easy mistakes that we can make in doing logical derivations. Humans are not naturally good at applying complex, multifaceted rules in an intuitive way. You might have noticed this in the course of your everyday life, but you will certainly notice it in the course of doing logical derivations. And hello, this is Editing Adam here. I just want to mention Mark Jago, who is an actual logician and has his own YouTube channel, Attic Philosophy, which you might want to check out. Especially this video, where he talks about how people do natural deduction wrong, and it's got a really interesting bottom-up approach to doing derivations. So there we have a quick run through of De Morgan's laws and how to derive them and why those derivations work. I hope you found this interesting, and I'll see you in the next part of the logic series when we start to look at quantifiers.